Hello, I'm Michael Wunsch. I'm the plant pathologist at the North Dakota State University Carrington Research Extension Center. I'd like to take a moment to share what we have learned about fungicide droplet and its impact on Ascochyta blight management in chickpeas. We started this research on the basis of parallel research conducted in soybeans for white mold management. What we found, now white mold is a disease, of course, that develops in the interior of the soybean canopy, and what we found is that we sharply increased the yield gain conferred by the fungicide and the disease management conferred by the fungicide by calibrating fungicide droplet size relative to canopy closure. So the denser the canopy at the time of application and the taller the canopy, the coarser the droplet size we need to apply. And so looking at chickpeas, I thought, well, I wonder if chickpeas are going to respond the same way, because in these wetter years when that chickpea canopy closes, it'll close really densely, and then when we apply that fungicide during pod fill, we have to get that fungicide into the interior of that canopy in order to protect the pods. And so then you have a situation very analogous to soybean white mold, where you have a target inside of a dense canopy that you need to protect. Before we go into the methods or the results, let me back up for a second, just explain a few concepts. When someone talks about droplet size, they're talking about the diameter of the droplet. So let's take an example here of a 500 micron droplet. Now, if we were to cut that droplet size in half, the 250 micron droplet, well, how many droplets do we have for that same amount of volume? It's actually 8, not 2. And that's because we're talking about volumes now. Okay, so you take a droplet size in half, you suddenly have 8 times as many droplets. You cut it in half again, you get another 8 times as many droplets, i.e. 64 times as many droplets. And this matters for fungicides. A contact fungicide only protects the spot where it lands, and a locally systemic, i.e. a modern fungicide, can move upward from the point of deposition to some degree, but can never move downward from the point of deposition. So you take that one 500 micron droplet, and it gets deposited on the leaf. It can protect, if it's locally systemic, it can protect from that point of deposition upward to some degree. And so on this leaf on the top of this slide, the best it could do is to protect about 2/3 of that leaf. And that's only if it's able to move all the way to the tip, which is no guarantee. Now, if you take that same volume and apply it with a 250 micron droplet, suddenly you have 8 droplets. And let's say all 8 of those droplets, that same volume gets on that leaf. By pure chance, you're going to get better coverage, better deposition, a better pattern, a spray pattern on that leaf, as long as the droplets can get to that leaf. Okay, and so if you look at the deposition pattern we have here with a locally systemic fungicide, you probably have 90-95% of that leaf covered, because again, anything from the point of deposition towards the tip of that leaf would be able to be covered by local systemic movement. Okay, but if you cut the droplet size in half again, and now you have the 64 droplets, and you apply and you assume that all 64 of those droplets, the exact same volume, gets deposited on that same leaf. And now you have a situation where you have a potential for the entire leaf to be fully protected. Now that works if the fungicide can get to the leaf, right? And so the big problem that we have with the fine droplets as the canopy starts to close is that they don't have velocity. And that's true even if you apply them with lots of pressure. So that pink line in this graph shows the velocity of the droplet relative to the droplet size and the pressure at which it was applied. And so you can look at the 58 psi versus the dark blue, which is 44 psi, versus the light blue, which is 29 psi. And what you can see is the fine droplets just don't have the velocity, even if you apply them with high pressure. As you move to a medium droplet or a coarse droplet, now you start to get velocity. And of course, those fine droplets drift off target very easily, which certainly does not lend itself to deposition within a canopy. And the propensity towards drift and the lack of velocity means that those finer droplets have a very hard time getting inside a dense canopy. Think about a ping pong ball versus a lead ball. Okay, you throw them with the same amount of force, and that lead ball is going to have a much easier time getting through some dense materials, right? And so same concept here with spray droplets. Okay, so how do we do the testing? Okay, we did testing with both TJet and Wilger nozzles. We use extended range flat fan nozzles from TJET simply because it worked well in the study relative to our driving speeds and our spray volume. I would expect parallel results across the entire lineup of tips from TJET. We selected the pressures and the nozzles on the basis of the TJET catalog and the Wilger catalog, and then we double checked the spray output with Winfield. We had them test the actual droplet size spectrum using their laser-based system in their wind tunnel in the R&D facility in River Falls, Wisconsin. What we found is that what we considered, what the catalog said would be a fine droplet with TJET was actually on the fine end of the medium spectrum, and what the catalog said would be a fine droplet with Wilger was in the fine spectrum, but again on the coarser end of the fine spectrum. So what these results would say is that the differences in droplet size that we showed in our results will actually be more pronounced if you're spraying with a droplet in the middle or the finer end of the fine spectrum, okay? Because we were spraying with fine droplets that were right on the cusp between fine and medium, whether it was Wilger or TJET. What you can see is that the medium and the coarse droplets check out exactly, okay? By all means, the integrity of the study is intact because you can see really big changes in the droplet size as you go between these nozzles. So we go from finer to coarser, okay? A little bit more about the methods. We had a PTO-driven tractor-mounted sprayer that we used for these applications. It's equipped with a pulse width modulation system. That pulse width modulation system allowed us to maintain a constant driving speed of 15 gallons an acre. Constant driving speed of 10 or 10.5 miles an hour, depending on the study, and a constant spray volume of 15 gallons an acre. Okay, and so as we went across treatments that differed in output, we were able to maintain that same spray volume and that same driving speed just by changing pulse width, okay? And we assessed Ascochyta a few times during the season. It's reported on a 0 to 100 scale corresponding to the percent of the canopy diseased over the bloom and pod fill period, okay? Additional details on the methods are presented here. The exact pulse widths are shown. One of the advantages of using the Wilger nozzles is that you're able to maintain the same spray output as you change droplet size, and so you don't really need to change pulse width much to maintain the exact same driving speed. And so pulse width is essentially constant across the Wilger droplet size treatments. And the actual pulse width utilized, the actual nozzles utilized, the number of experimental replicates, all the planting dates, harvest dates, all that's presented here. Okay, we manually calibrated our pulse width. We have an older system, the capstan pulse width system that allows you to manually set the pulse width. And what we did was we ran this sprayer for exactly 10.0 seconds with the fungicide in the tank immediately before spraying the treatments. We collected the output in these milk jugs, and then we measured the output. Okay, every nozzle measured. And if the output was not perfect, then we changed the pulse width and we measured again until we got it perfect. Okay, so we had our exact 15.0 gallons an acre spray volume, and then we of course sprayed at our precise driving speed. That application was made with this tractor-mounted sprayer. This picture and the corresponding video that I'll show you in a moment is taken in soybeans, but the same methods were done in chickpeas. You can see a driving pass that's smoothed out with a special cultivator that just cultivates the tire tracks, and we smooth it out so that the boom does not sway, and so that we have consistent 20-inch height above the canopy for the 110-degree TJET nozzles and a consistent 19-inch height above the canopy for the Wilger nozzles, as recommended by the nozzle manufacturer. Now, what you'll notice is that the driver operator, he turns on the sprayer between that white and blue flag, and then on the back end of the blue flag, he turns it off before he gets to the next color flag. The treatment plots are between flags of the same color, okay, and those transition zones between flags of different color are non-harvested. They're not assessed for disease. They exist purely for turning on and off the sprayer so that the driver operator can maintain his speed and make sure he doesn't spray the neighboring treatment plot. Hello, I'm Michael Bunch. I'm a plant pathologist at North Dakota State University Carrington Research Extension Center. I'd like to take a moment to share what we have learned about fungicide droplet and its impact on Ascochyta blight management in chickpeas. And there you can see he turned off that boom before he hit the next plot, which was marked with that yellow flag. Okay, you can see we're spraying a 10-foot width with full nozzle overlap, yeah, those are our methods. Okay, let's go into results. These bar graphs show the results across 2 chickpea varieties assessed 1 year and 4 chickpea varieties assessed another year. Okay, so 2 years of testing across a total of 6 varieties. And what you'll see is we compared to a non-treated control and then 6 different droplet size treatments. These are indicated with a slash. So the droplet size indicated before the slash is the droplet size we utilized when more than 10% of the ground was showing between the chickpea plants. And this was a pure visual assessment taken across multiple locations in the field because there's always variability, and these studies are big. So just like your commercial fields, there's variability out there, okay? And we're taking the average. So if on average more than 10% of the ground was showing between the rows, i.e. less than 90% canopy closure, then we applied the droplet size shown on the first before the slash, okay? And then if the canopy closure was averaged more than 90%, i.e. less than 10% of the ground showing between the plants, then we applied the droplet size after the slash. So fine followed by fine means we applied fine droplets all season irrespective of canopy closure. Fine followed by medium means that we applied fine droplets when the canopy was open, okay, less than 90% closure, and then medium droplets after the canopy began to close, i.e. once the canopy closure hit 90%. And fine followed by coarse, again, fine droplets when the canopy was open, then coarse droplets in all applications made after canopy closure hit 90%. Okay, in this case, we applied the same fungicide sequentially all season. It is good to rotate modes of action, but we did this simply to simplify the study and simplify the analysis. Okay, and so we have Proline applied alone. This you should expect any modern locally systemic fungicide applied alone to perform like this. Okay, so Proline or Provisol or Marevis Top, any of these locally systemic fungicides applied alone without the tank mix chlorothalonil partner should perform like this. Then the other study we tested Proline tank mix with Bravo weather stick chlorothalonil, and you should expect any of these locally systemic fungicides tank mixed with chlorothalonil to perform similarly. Okay. What you can see right away is that we achieve statistical separation, okay, with the locally systemic fungicide applied alone, optimized when you sprayed with fine droplets when the canopy was wide open, and then medium droplets as the canopy approached closure or was closed. And when we use that tank mix with chlorothalonil, we optimized with fine droplets when the canopy was wide open, and then coarse droplets when the canopy was either approaching or at full closure. Okay, so those are surprising results because you would expect that the contact fungicide chlorothalonil would need a smaller droplet size, right? But if you look at the response to calibrating on droplet size relative to canopy height, you can see that these results do appear to be very rigorous. So as the canopy gets taller, it gets harder for a fine droplet to get into the middle of that canopy or the bottom third of the canopy. For chickpeas, for our pod, where our pods are usually located, you're usually looking at kind of that, the top 60% of the canopy is what you need to protect, okay? And the taller the chickpea plant, as that canopy closes, the harder it is going to be for a fine droplet to get inside. And what do you see? So that top, the scatter plot here on the top is the response, the yield gain conferred by the fungicide associated with applying with fine droplets when the canopy is open, and then medium droplets when the canopy hit 90% closure, so is at or near closure. Okay. The yield gain conferred by the fungicide by using a fine followed by medium protocol versus fine droplets all season relative to the chickpea canopy height at the time that we hit that 90% closure. And what you can see is that the response to droplet size is consistently positive, but it gets stronger the taller the chickpea canopy is, which is exactly what you would expect. Okay, so that's the locally systemic fungicide alone. And again, optimized with fine droplets when the canopy is open, medium droplets when the canopy is approaching closure or is closed. Okay, and the degree of the yield gain to applying with fine followed by medium versus fine droplets all season is contingent on the canopy height. Okay, now you look at that tank mix and you see even stronger correlation of the yield gain conferred to applying with fine droplets when the canopy is open, followed by coarse droplets as that canopy is at or near closure, okay, with the versus fine droplets all season. With the gain from applying to calibrating your droplet size relative to canopy closure, increasing with chickpea canopy height. Again, the canopy height shown here is that height that existed when we were at that first application made after the canopy hit minimum 90% closure. Okay, and so again, this is exactly what you would expect, and you can see a very strong correlation here. And so it is very unlikely that we saw these results by accident. Okay, these results appear to be very rigorous. Okay, what about Wilger nozzles? Okay, what you can see here is that we have no statistical separation. Testing was done on the same 6 varieties across the same 2 years at the same location, and no statistical separation. We do have some trends, however, with some treatments numerically higher on the yield. So let's look at those treatments relative to canopy height. And so again, this is comparing that droplet size program versus applying with fine droplets all season. And the canopy height would be the canopy height that the chickpeas are at when they reached 90% closure or more. Okay, so that first application where we had 10% or less of the ground showing between the canopy, that was the canopy height. Okay, and what you can see is that for that locally systemic fungicide applied alone, Proline, what you can see is that we had absolutely perfect correlation in terms of the yield gain from applying with medium droplets all season versus fine droplets all season relative to the canopy height. Again, canopy height assessed at that first application where we averaged minimum 90% of the ground covered by the canopy. Then Proline tank mixed with chlorothalonil, so this is the locally systemic fungicide, tank mixed with the contact fungicide. Our yield gain to using in this case, the optimum was medium droplets in the first application, followed by coarse. Once the canopy closure, averaged at least 90%. Okay, the yield gain was correlated again with canopy height, with the gain to applying with medium when the canopy is open, and coarse when the canopy is at or near closure, increasing with the canopy height. Okay, there's a bit more noise in this scatter plot, but it shows the same relationship. And the last thing I would mention, though, is that if you look at the percent yield gain here, and also the numerical yield gains, you'll see that they're lower than we saw in the corresponding TJET studies. Okay, and these studies were conducted in parallel. Okay, and under the same environmental conditions. So what this suggests is that response, and also the lack of statistical separation, suggests that the response to droplet size with Wilger is lower than with TJET. Okay, so what have we learned? Okay, what these results strongly suggest is that the standard recommendation of applying fungicides with fine droplets all season, irrespective of canopy characteristics, is not optimal for Ascochyta blighted chickpeas, even when applying a contact fungicide tank mix with a locally systemic fungicide. And actually, if anything, it's even more suboptimal for that tank mix. Okay, and so these results suggest that to figure out what droplet size you need to be using, you need to first make the decision based on the nozzle manufacturer, because you notice the optimums here were different by nozzle manufacturer. Second, you need to evaluate what fungicide you're applying, right? Because the optimums are different whether you're applying a locally systemic fungicide alone or a locally systemic fungicide tank mix with chlorothalonil, Bravo Weather Stick or generic. Okay, and I would expect that these optimums are going to be exactly the same across fungicides with the same systemic movement profile. Okay, so basically a local across all locally systemic fungicides, this would be Proline, Provusol, and Maravus Top, for instance. These will all perform similarly, and when you tank mix these with Bravo Weather Stick, that tank mix, irrespective of whether that tank mix is done with Provusol or Maravus Top, should respond similarly to droplet size. Okay, and with T-jet nozzles, by calibrating our droplet size relative to the type of fungicide applied and the canopy closure, we increase the yield gain conferred by fungicides by 3 to 52%, and with Wilger nozzles, the yield gain was just 0 to 17%. So, again, droplet size needs to be calibrated relative to the nozzle manufacturer, the type of fungicide being applied, whether it's a modern locally systemic or a tank mix with Bravo Weather Stick or generic and the locally systemic, and the degree of canopy closure. The amount of yield gain you can confer that you can expect from making that change in droplet size as your canopy closure hits 90% is going to increase with canopy height. Okay, and the response to droplet size is higher with T-jet nozzles than Wilger, i.e. the penalty to getting your droplet size wrong is higher with T-jet nozzles than Wilger. Okay, and now these results of the differential performance of these two nozzle manufacturers is actually consistent with what we've seen in other crops. On soybeans, the response that will be done the most extensive testing of droplet size, the response to calibrating droplet size relative to canopy closure gave us yield gains of 50 to 100%. Yield increases, i.e. the amount of yield gain conferred by the fungicide increased by 50 to 100% by calibrating droplet size relative to canopy closure with T-jet nozzles. With Wilger nozzles, we increased on average about 50% the yield gain conferred by the fungicide by calibrating your droplet size relative to canopy closure, i.e. double the profitability of our fungicide application by getting our droplet size right with T-jet nozzles, but we only gained about 50% increase in profitability of our fungicide applications with getting droplet size right with Wilger. So what we found on soybeans is that the penalty to getting your droplet size wrong was lower with Wilger than T-jet, but on both of them we could improve fungicide performance by getting our droplet size right. The other thing we saw in soybeans is that the droplet size optimum was different between the two nozzle manufacturers. Okay, and on soybeans at least, the droplet size optimum for Wilger was typically one step higher than T-jet. So if medium's optimized on T-jet, then coarse is optimized with Wilger. Okay, and so we're seeing something similar here in chickpeas, where the penalty to getting your droplet size wrong with Wilger appears to be lower, and then the droplet size, the optimum droplet size program with Wilger may be slightly different than T-jet. So before I close, though, I want to stress these are preliminary recommendations based on a research progress that is in progress. Now, the results make lots of sense. What they suggest is that as that canopy closes, we need a coarser droplet size to get inside in order to protect our pods, where, of course, we need to protect to ensure that we have high seed yield and quality under Ascochyta pressure. Okay, and they also make even more sense by the fact that you can see that the taller the chickpea canopy, the more the response to that droplet size. But yet they are still results just from 2 years of testing. And 2025, we're expanding this testing to look at a larger number of varieties, and thus we're doing the testing with even more rigor. And hopefully at the end of the 2025 season, I can deliver definitive, rigorous recommendations. At this point, I would consider these preliminary recommendations that make lots of sense but need to be confirmed. With that, I'd like to thank my staff, Aaron Faust, Jesse Hafner, Gabby Henson, Soren Collis, and all of our seasonal workers. The extraordinary dedication of these individuals makes this research possible. I'd also like to give very sincere thanks to the Northern Pulse Growers Association. These are your checkoff dollars, the USDA Specialty Crop Block Grant Program, and the North Dakota Crop Protection Product Harmonization and Registration Board. These last two organizations are administered by the North Dakota Department of Agriculture. The funding from these three sources made this research possible. This is how we pay our staff, our research support staff. This is how we pay for all the supplies associated with conducting these studies and all the repairs to our equipment. I'd also like to give very sincere thanks to the private companies who do contract testing with us, because the funds from that contract testing allows us to have the flexible research dollars needed to be able to invest in our equipment. So that tractor you saw in that video, that sprayer, our plot combine, and our other very important critical pieces of equipment, we were only able to purchase through the funds generated by doing contract testing for companies. Thank you for your time and attention. I hope that this research is of value to your operations.